Pluto, the enigmatic dwarf planet at the outer reaches of our solar system, is causing a stir in the astronomical community. Recent reports hint at a possible encounter with Neptune, raising concerns among scientists and space enthusiasts alike. Renowned experts, including Neil deGrasse Tyson and MIT's Oahu, have sounded the alarm about the potential consequences of this celestial collision. But how did Pluto end up on a collision course with its distant neighbor, and what could this cosmic clash mean for us here on Earth? Let's explore this unfolding event. Once considered a full-fledged planet, Pluto was later reclassified as a dwarf planet due to its unique orbit. Despite this change, it continues to fascinate and intrigue astronomers. Recent predictions by prominent scientists highlight a worrying proximity between Pluto's orbit and that of Neptune. These experts warn of a possible collision between the two planets, posing a significant threat to Earth. Pluto's orbit around the Sun is unique in our solar system. Its orbit spans 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the highly elliptical shape of its orbit, a departure from the nearly circular orbits of the major planets. In addition, Pluto's orbit is inclined at 17 degrees to the ecliptic plane, making its orbit steeper than that of the other planets. A notable aspect of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational influences exerted by other planets. The examination of Pluto's orbit commenced shortly after its discovery, presenting a puzzling trajectory for astronomers. Unlike the majority of planets, whose orbits align relatively close to the ecliptic plane, Pluto's distinctive features include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these intricacies serves as evidence of the complexities inherent in space mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem elucidates the intricate interplay of their paths and gravitational poles. Terms like AIML libration, latitude libration, and the VZK oscillation contribute to unraveling this celestial puzzle. Astrophysicists assert that a muffle libration responsible for maintaining planets in their orbit plays a vital role in the context of Pluto and Neptune. This term signifies that when Pluto intersects Neptune's orbit, it is positioned at least 90 degrees away from Neptune, crucially preventing potential collisions. Latitude libration ensures that when Pluto approaches Neptune or other giant planets, it is situated significantly above their orbital plane, providing an additional layer of protection against collisions. The VZK oscillation explains why Pluto's orbit around the Sun appears unusual but remains smooth over time, despite apparent randomness in space. Numerical simulations in the late 1980s showed that, despite its stable properties, Pluto's orbit is technically chaotic, with small initial deviations leading to significant differences over millions of years. However, Pluto's unique orbit maintains stability over incredibly long time scales, keeping the chaos in check. Recent computer simulations have improved our understanding of how large planets such as Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune's unique relationship with Pluto, it completes 3 orbits to Pluto's 2, contributes significantly to the stability of Pluto's orbit. In addition, Jupiter's immense gravitational pull exerts a significant influence, while Saturn's influence, although smaller, also plays a role. Through extensive testing, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure Pluto's safe and stable movement through space for billions of years. These phenomena are essential for maintaining the order and predictability of celestial motion in the universe. Without these mechanisms, the solar system would be prone to greater chaos and unpredictability, potentially leading to collisions or ejections of Pluto's orbit from stable orbits and causing ripple effects on other celestial bodies. Understanding Pluto's orbit is particularly important in the context of discussions about a possible collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the solar system. The case of Pluto illustrates how apparently unstable orbits can reach equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Continued observation and study of these phenomena is essential to better understand our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos vividly illustrates the sensitive dependence of a body's orbit on its initial conditions. As shown in the case of Pluto, even small variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Computer simulations have helped scientists understand how Pluto moves in space. By making small adjustments to these simulations, astronomers can observe how small changes can have a significant effect on Pluto's orbit. In the late 1980s, these simulations revealed a fascinating aspect of Pluto's orbit. Despite features such as AIML and latitude libration contributing to its stability, Pluto's orbit can still exhibit unpredictability. Even a tiny initial difference in Pluto's position or speed can lead to significant changes in its orbit over many years. Despite this inherent chaos, Pluto's orbit remains stable for an unusually long time, over billions of years. This suggests that Pluto's journey around the Sun follows a structured order beneath its apparently erratic appearance. Predicting cosmic events, especially with planets such as Pluto that have unpredictable orbits, is quite challenging. The inherent unpredictability of these systems makes long-term predictions uncertain. Numerical simulations help us to understand and predict the future paths of celestial bodies, but they also reveal the limits of our predictive capabilities. These models rely heavily on accurate initial conditions and simulate complex interactions. Even a small error can lead to significantly different results, making accurate predictions difficult. The chaotic nature of celestial orbits, such as that of Pluto, reminds us of the ever-changing nature of the universe. While we've made progress in understanding the universe, the case of Pluto highlights how limited our knowledge remains. Understanding the gravitational influences of giant planets on Pluto's orbit provides valuable insights into the wider dynamics of the solar system. It shows how the presence and position of each planet can affect the stability and orbits of other bodies in the system. Despite these complex forces, leading astrophysicists are concerned about a possible collision between Pluto and Neptune. This raises the question of why such a collision, which seems unlikely given these complex dynamics, is now a top concern. Neil deGrasse Tyson, a well-known astrophysicist, offers a special viewpoint on the mysteries of our solar system, particularly regarding Pluto. Tyson, famous for reclassifying Pluto as a dwarf planet instead of a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is always evolving. Tyson sees Pluto's reclassification not as a demotion, but as a necessary adjustment to our increasing knowledge about the various objects circling the Sun. His approach to celestial mechanics involves continual learning and adaptation. He views the complexities of orbits like Pluto's as a reminder of how much more there is to discover in space. Tyson believes that the allure of these unknowns is what makes astronomy so captivating. Additionally, Tyson is aware of how space-related events and discoveries shape public interest in astronomy. He thinks occurrences like Pluto's reclassification and its unusual orbit are opportunities to capture the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes counterintuitive aspects of space mechanics, Tyson aims to foster a deeper understanding and appreciation of the cosmos. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and mysteries of the universe. Working with other scientists, Tyson is actively warning the public about the potential dangers of Pluto's unpredictable orbit. After extensive study of Pluto, he has raised concerns that the three-body problem could be a real threat, suggesting that a collision with Neptune is long overdue. In addition, Tyson emphasizes how such a collision could upset the balance of the universe, with catastrophic consequences for Earth. A collision between Pluto and Neptune would be an unusual and catastrophic event in our solar system. This collision would release a massive amount of energy, which would probably break apart Pluto due to its smaller size and icy composition. Debris from the collision could be scattered throughout the solar system, posing a potential threat to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory and science popularization, offers a unique perspective on this scenario. His views on the future of space exploration and the link between celestial mechanics and theoretical physics provide deep insights into phenomena such as Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, Kaku says, can provide crucial insights for future space missions. This knowledge can help navigate the solar system more effectively, predict potential hazards, and plan missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to the study of other celestial bodies, providing a blueprint for approaching and understanding distant worlds. When discussing the physics of the planets, Kaku often emphasizes the deep connection between celestial mechanics and theoretical physics. He believes that the motions and interactions of the planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are linked to fundamental principles of physics. Kaku's work in theoretical physics, particularly string theory, aims to understand these principles at the most fundamental level. He suggests that studying the complexities of celestial mechanics, such as the orbit of Pluto, is one way of approaching an understanding of these deeper cosmic laws. For Kaku, Pluto's movement around the Sun is a reminder of the hidden patterns that govern the universe, patterns that theoretical physics seeks to unravel. Kaku is also cautious about the possibility of a collision between Pluto and Neptune,
Pluto,
drawing
the enigmatic
parallels with
dwarf
catastrophic
planet residing at
scenarios
the
in
outer
physics.
reaches of our solar system,
He notes that
is
if a
stirring up
collision were to
excitement
occur,
within the
the
astronomical
energy
community.
released could have
Recent reports
unpredictable
hint at a
consequences
possible
for the solar
encounter with
system,
Neptune,
including
raising
possible
concerns
shifts
among
in planetary
scientists and
orbits,
space
or
enthusiasts
even
alike.
destabilization of the
Renowned
solar
experts,
system's structure.
including Neil deGrasse Tyson
This
and
cosmic
Michio
collision,
Kaku,
says
have
Kaku,
sounded alarms
could
about the
provide
potential
a rare
consequences of
opportunity
this
to test
celestial
theories
clash.
about
But
gravitational
how did Pluto
interactions,
end up on a
the nature
collision
of
course
planetary
with its distant
collisions,
neighbor,
and the
what might
mechanics
this
of
cosmic
celestial
collision
bodies.
mean for us here on Earth?
Kaku believes that
Let's
such an event
explore
would
this
provide
unfolding
invaluable data
event.
for scientists
Once
to
considered a
understand these
full-fledged
dynamics
planet,
in real time.
Pluto was later
Despite the
reclassified
potential
as a dwarf
catastrophe,
planet due to its
Kaku
unique
suggests
orbit.
that humanity could
Despite
still
this
find
change,
ways to learn
it
from the
continues
event
to captivate and
turn it into
engage
an opportunity
astronomers.
to expand
Recent
our
predictions
understanding
from
of
prominent
space.
scientists